Hello, welcome to our channel for probability and statistics. In this video, we will talk about three distributions arising from normal distribution. So these three distributions are chi-square distribution, t-distribution, and f-distribution. They are also often used with three types of testing in statistics. So first we will talk about chi-square distribution. So we know if say 1, say 2 to say n are independent standard normal random variables, so which means, for example, say 1 is normally distributed with mean 0 and standard deviation 1. So say 1 square will follow so-called chi-square distribution with 1 degree of freedom. And x, which is the summation of say 1 square, say 2 square, until say n square, that this variable we called follows a chi-square distribution with n degrees of freedom. So it's quite clear. So chi-square distribution is related to a standard normal variables square, right? That's why we call square in chi-square distribution. And this figure shows several density curves for chi-square distribution with respect to different degrees of freedom. So, for example, if we have degrees of freedom equals 5, so the curve looks like this one. And then the use of chi-square distribution mostly in two areas. The first is in regression. In regressions estimation, so we call SSR, which is sum of squared residue divided by the sigma square, which is the random variables variance. So this statistic has a chi-square distribution with n minus 1 degrees of freedom, where n is the sample size in regression. And another widely used statistics for the chi-square distribution is independent tests of two categorical variables. So this is a contingency table between two categorical variables. So this is the variable A, this is variable B for the different values. And the white area represents the counts for each category relationship. And the total number of these counts are sample size, right? So this table is used to test if these two categorical variables are independent. So we can create a statistic called chi-square is the sigma of observed counts minus module counts, then take a square divided by module counts. So observed counts are quite clear, is the counts in this white area. And the model counts, model ij, for example, model ij, this one modeled counts should be the ratio of this item in the row times the ratio of this item for this column. Then these two ratio multiplication then times the total counts of sample size. So this is the model counts. So this statistic will have chi-square distribution with R minus 1 times C minus 1 degrees of freedom, where R and C are the columns, how many columns and how many rows. And for the chi-square distributions density curve, so we will first find the density function for the gamma distribution. So this is a gamma distribution. And for the positive variable, the density function is beta alpha times gamma alpha, where gamma is the gamma function. In the denominator, then times x alpha minus 1 in power times is x divided by beta minus in power. So this is a gamma distribution, and chi-square distribution is also a special case of the gamma distribution when beta equals 2 and alpha equals v divided by 2. So where v is the chi-square distribution's degrees of freedom. So this is the chi-square distribution's density function. And the mean of a chi-square distribution is v, which is the degrees of freedom. And the variance is 2v. So this is a chi-square distribution density curve, and if we let the alpha to the right of this critical value, chi-square alpha, so we can find from this table for the degrees of freedom and alpha, then we can find critical value, this value. And alternatively, from this differential critical value and with degrees of freedom, we can also find alpha. So these two processes often used in chi-square tests. So next we show two examples using this table. Example 1, you determine the probability of chi-square distribution with 26 degrees of freedom less than 30. We will find the probability of this critical value less than 30. So we check the table for the variable 30 and the degrees of freedom. We will get the probability for alpha is 0.27. So we know this value is 30, and we know the degrees of freedom is 26. So we can find alpha is about 0.27 for this blue area. So the probability for this critical value less than 30 is the white area, which equals 1 minus alpha. So the result is 0.73. Example 2, the problem is that you want to find chi-square distribution's random variable for alpha equals 0.05 and degrees of freedom is 15. So we also check the table. For degrees of freedom 15, we find the degrees of freedom 15 and alpha is 0.05. We can find this critical value. So the result is 24.996. Next, we will talk about t-distribution. A t-distribution is widely used for the hypothesis testing of the population mean in the small sample case. A t-distribution is also called the student's t-distribution. So say if we want to test the population mean, so when sample size is very large and we know the population variance sigma square. So this say which is the sample average minus the hypothesis population mean and divided by the population standard deviation divided by the sample size square root. So this statistic called Z, when n is very large, has standard normal distribution. with mean 0 and standard deviation 1. But in the case where n is not very large, so usually under 30, and the population variance is not known, so we have to use the sample variance S squared in calculation of this statistic. So we say t equals x bar sample mean minus the hypothesis population mean divided by the sample standard error divided by the square root of sample size. And this is the calculation of the S squared. So this t statistic, we go further to manipulate it. We can get equals c divided by v divided by n minus 1 take a square root. So where z is the same as the previous page, which has standard normal distribution. And v here equals n minus 1 times sample standard error divided by the population unknown variance. So this term will have chi-square distribution with n minus 1 degrees of freedom. So the t equals c divided by v divided by v, which is degrees of freedom, take square root. So this term t follows a t-distribution with v degrees of freedom. So you can see a t-distributed random variable actually is a standard normal random variable divided by a chi-square random variable divided by its degrees of freedom, then take a square root. And this is the t-distribution's density function. And this figure shows several t-distributed density curve. I can see if the degrees of freedom is very large, then the t-distribution is same as a standard normal distribution. This table is also called t-distributions table for calculation of critical value. So from degrees of freedom and alpha, which is a blue area, so you can find the critical value T alpha. And on the contrary, we can find alpha from the given T value. So we show an example. A chemical engineer claims that the population mean yield of a certain batch process is 500 grams per milliliter of raw material. To check this claim, he samples 25 batches each month. If the computed T value falls between minus T005 and T005, he is satisfied with this claim. So what conclusion should he draw from a sample that has a mean sample average 518 grams per milliliter and a sample standard deviation S equals 40 grams? Assume the distribution of yields to be approximately normal. So the solution is from the table for the t-distribution, we can find critical value T005 equals 1.711 for 24 degrees of freedom. So from this table, we can find this critical value from the alpha and degrees of freedom, right? Therefore, the engineer can be satisfied with his claim if a sample of 25 batches yields a T value between minus 1.711 and 1.711. So if in the hypothesis testing, if this is correct, then we get a t value from the formula, then filling in the sample information. This t value equals 2.25. And this value is much larger than 1.711. So we will reject the hypothesis that population mean is 500 because this is very small probability event which occurred. And from this critical value and with degrees of freedom 24, we can get the alpha p-value is 0.02. If we look at this figure again, we get the t statistics 2.24, and this t alpha is 1.71. So t from the sample 2.24 is much larger than this value, and which leave the blue area we call the p-value is much less than alpha. Alpha is 0.05, and we get this blue area to the right is about 0.02. So this is called, we reject the null hypothesis, and actually the value of this t computed from the sample is more reasonable when the population is larger than 500. So the engineer is likely to conclude that the process produces a better product than he thought. So now we will talk about fdistribution and ftest. If chi-square-n and chi-square-m are two independent random variables which follow chi-square distribution with n and m degrees of freedom. So a division chi-square-n divided by n divided by chi-square-m divided by m. So this ratio of chi-square variable divided by its corresponding degrees of freedom, called f and m, is said to have an f-distribution with n and m degrees of freedom. So you can see chi-square distribution and f-distribution quite closely related. And we can also get probability of alpha if chi-square distributions variable larger than a critical value. So we take a look at these density curves for f-distribution. If in f-test for the one side, usually, for example, we will test if the population two variance is the same, then we get the test statistic if in this area we say the test is significant, and the null hypothesis of two variants are the same will be rejected. And similarly, for the two-sided test, if we got the test statistic from the sample in these two white area, we will also reject hypothesis that two variants are the same. So next, you can see hypothesis testing of comparing two variants with f-test. So usually, the null hypothesis is two variants are the same, and alternative hypothesis is variance not the same. Then we get the sample variance, then take the division of these two. Then this value f have f-distribution with n1 minus 1 and n2 minus 1 degrees of freedom. Should be note, S1 have to be up and S2 square in the denominator. That's why we call the V1 is n minus 1 and V2 is n2 minus 1 degrees of freedom. So next we show an example. An experiment was performed to compare the abrasive wear of two different laminated materials. And 12 pieces of material 1 were tested by exposing each piece to a machine measuring wear. 10 pieces of material 2 were similarly tested. In each case, the depth of wear was observed. And the samples of material 1 give an average wear of 85 units with a sample standard deviation of 2, while the samples of material 2 gave an average of 81 with a sample standard deviation of 5. Assume the population to be approximately normal. We assume that the two unknown population variants are equal. Were we justified in making this assumption? Use 0.1 level of significance. So this is a question of testing if the two populations have same value of variance. So the solution is let sigma 1 square and sigma 2 square be the population variance of the abrasive wear of material 1 and material 2. Then we form the null hypothesis is these two variants equal. And we form alternative hypothesis is they are not equal. Then we set alpha level 0.1. Then from the f-distribution table, we can find f critical value for the 0.05, 9 degrees of freedom equals 3.11. So this is a two-sided test, and we find this critical value 3.11. So this white area is 0.05, and this F distribution have 11 and 9 degrees of freedom. So next we will find this critical value also. We will leave the white area here is also 0.05. So we have 3.11 for one critical value, and the other critical value can be found from this formula. So other critical value on the left side is 0.34. So the null hypothesis is rejected if we get the sample f less than this value or larger than this value. So we calculate f equals s1 square divided by s2 square. Then s1 square is 16 and s2 square 25. Then f equals 0.64. So you can see these two critical values here and 0.64 in the white area, not in blue area. So which means the test is not significant and we do not reject H0, then conclude that there is insufficient evidence that the variance will differ. In other words, we will hold the null hypothesis that two variants equal. Thanks for watching.